So here is our schedule. We are here Wednesday doing more graphs. Tomorrow is Halloween, and Friday is challenge 3 is due. So yes.
Do we get bonus points if we show up prior to the captain?
I don't think so. You could talk to the TAs though, maybe. I don't know. That's their call, I think. Now, if we had class on Halloween, then that would be a different story. That could be like an exam or something. But fortunately, the calendar does not allow it. So challenge 3, if you have not looked at it, it would be a good time to look at it and to sign up for a demo. So the code for challenge 3 is on Canvas. And just to show you what that looks like. So usually I give you like a version of the code that we write in class together. And if you remember, we did write, like a long time ago, binary search trees together. But this time, one of your TAs, Jacob, has written the base implementation for you. And so that's what I've given you on Canvas. It's pretty much the same as what we wrote in class. And so everything is there. So I know like that the challenge document says like you need to write the public methods and you need to write like a couple of things. You need to add it. It's already there. I don't know if I gave you the wrong version that was already done or something, but either way, it's like not important code and it's stuff we've written before, so I think you're fine. But this code is all written for you, and the thing that you'll need to be able to take out and re-implement is over here in this bst.cpp file, and that is the remove code. And so that function starts up here, line 69, and you can look through that, and then you'll see down here on line 97, it says start of demo, and then all the way down through here.
Well, we got to type on it.
So you'll need to know all of this. It's possible that Jacob or whoever's grading you will ask you to write this entire function. I'm not sure that they will because of time, but it's a lot of lines of code, especially when it's blown up like this. But if you remember back when we looked at binary search trees, so there are just like 3 different cases to handle whenever you delete a node from the binary search tree. And so that's all this is doing, is just handling each of those cases. So if you will take some time and look through it, you can also look at either the slides from the binary search tree lecture or the video of that. Yes?
Is that all that's going to be covered in the demo?
Yeah,
Okay.
yeah. So that's all you'll have to do is this section with the removal of a node. And so, yeah, I would just look through this code for sure. Make sure you can compile it and run it. It's got all of the test code in there for you already in main.cpp. So all the stuff that's on that challenge PDF is in there. I will tell you, how many people are familiar with make files using make? Okay, a couple. Okay, so Jacob has set this up with a make file. So you'll see in the folder, you'll have bst.cpp.h, you'll have the node.cpp, node.h, and main.cpp, but you'll also see this make file. And so this is just a way to kind of ease the whole compilation process and help you adhere to standards. So when you build bigger and bigger projects, obviously there are lots of things that you want to happen. And if you remember, like when we do example code, usually in the comments I have like, you can compile this using like G++ and these flags and stuff to set the right version of C++ for the environment. So this file is just kind of a scripted way of doing that. It's very common. And so you can look at this file and you can see that it's got kind of these different things written out. And if you look at the documentation for make, it's all very straightforward. But you can read this and make sense of it. So like it's setting a variable to be like G++ in this case, another variable for remove. And so you set up these things like your source file. So there's that list of files that we would usually just list out manually. Or maybe if you have like your development environment set up all nice and neat, you'll just hit the play button and it does all this for you, that kind of thing. So for a make file like this, all you need to do is when you go into the directory for these files, if you'll just type make, it will run it. And you'll see here it's giving me an error because I don't have null pointer, because by default in this Mac environment, it uses a much older version of C++. And so you remember we add that flag that's like this. And so in the make file, you can add that here in this variable called cxx flags. And if you save that and then you rerun make, it will do that for you. And so it tells you what it's doing exactly, and it tells you what the output is, which is .bst in this case. And so you can run it there and you can see it. And also, Jacob has included some nice terminal tricks with like colors and stuff. So that's kind of cool. But yeah, so that's just a little bit of what the make file is about. You don't have to use it, but it is a good thing to know, especially if you're planning to go into like software development at any kind of scale where it's not just you or not just a handful of people. Make is a pretty common tool to help you build software. So, all right, questions about challenge 3?
Yeah.
Yes.
Mine was fun.
No, nothing?
Not yet.
No.
Only off that.
Okay. Yes. All right. So last time you remember we introduced this concept of a graph, which is kind of this broader linked structure. So if you remember, we've done trees, which were a linked structure that had some rules to them. And before that, if you think about linked list, that actually is technically a graph as well, right? Because it's just linked in a single fashion forward. So we defined what a graph was. Generally, the idea is that we have these vertices. They're sometimes called nodes or vertexes. We have these edges, which are links between them. And the idea is that they can represent some relationship between these vertices. We talked about the idea of having undirected versus directed graphs. And so we said that you can have either an edge that doesn't specify a direction you can go, or it can be kind of bidirectional when there's no arrows. That's usually how that's drawn. And if you have directed, you can have multiple edges to show back and forth. And we talked about restricting ourselves to what's called a simple graph. And simple graph just meaning that we don't have any loops within a vertex, so it can't loop back to itself. And we can't have like multiple edges that aren't just the directional ones. So today we will talk a little bit more about graphs.
I like graphs.
You like graphs? Graphs are great. And yeah, I mean, there's so many practical applications of graphs. And it's kind of, I don't know, because everything else that we've done is technically a graph as well, you can see how it is a broader thing that does a lot of work. So we were talking briefly about how we could represent a graph as a data structure, so how would we actually like code it, what would that look like? And there are a few different ideas about this. So we talked about starting with something called an adjacency list. And the idea here is that we would keep like an array or a vector, whatever you want to call it, a list. And for each vertex that we have in our graph, there would be a list of its neighbors. And so in this case, we're just labeling them with letters. And so like for vertex A, it just has a list that it's connected to B and E. And so that's a fairly straightforward, simple way of kind of representing all of this, all of the graph in memory in the computer. What's related to this is like, if you think about a more object-oriented approach, so like you define like a class for like a vertex, right? And it may have its own little private field that says like, who are my neighbors? Who am I connected to? It's the same thing as those lists of lists. It's just kind of distributed in a different conceptual way. And so you'll probably see, if you look at like existing implementations of graph data structures that some will use this when they're taking that object-oriented approach, where the lists are kind of within each vertex. And so this is pretty useful most of the time. Where it's not useful is if you're like building a bunch of graphs over the same set of vertices, maybe. You're kind of doing like, I don't know, like maybe batch operations or something, where you're not needing to like necessarily navigate through the graph in a way that's like you're going vertex by vertex. So we talked about kind of another idea about how we could represent one of these graphs, and that was the idea of an adjacency matrix. And so in this approach, what we do is we just make this 2x2 matrix, two-dimensional array, and we just put, for the rows, all of the vertices, for the column, all of the vertices, and just like 0 or 1, you know, if they're connected. And if it's an undirected graph, right, this will be symmetric, so you really only need like half of this. If it's directed, you can store, you know, like a value to say like which direction. Or actually, you can implement a scheme where you can say like this is to and this is from, right? It's just based on how you want to implement it. So what's not great about this that you can see already is that we need a guaranteed amount of at least however many vertices we have by however many vertices we have space, right, to store these. And if we have a bunch of vertices and very few edges, that's what we would call a sparse graph, and you will have very little in this big data structure that you've allocated memory for. So if you have a graph that's very well connected, everything's connected pretty much, then this makes a little bit more sense. So somewhat related, another approach you could take to doing this is like, say you have a, you can think of this as also a 2D array, a matrix. But I kind of think about this like if you're doing, if you've done like relational databases or something, this is kind of like the way you might think about it there, is you would have these columns like to and from for a directed graph. If it's undirected, that really doesn't matter. And then each row is an edge. And so like I've numbered these edges just for convenience. But you can see in the row you store kind of the start and the end, right? And you just make an entry for each edge that exists. So that's another approach you can use when storing this data. And then finally you can do what's called an incidence matrix. And it's a similar idea, but you have to store, you have all of the vertices as the columns, and then an entry for each edge. And still, each edge is only able to have, you know, 2 of these checked. Or if you have weights on your edges, you could store the weights in these slots. Might be convenient for that. So a variety of ways to do this. Probably the most common is just having the list of your neighbors stored with you, or if you have a really dense graph, then having that adjacency matrix stored. There's one other kind of case that appears, and that is what we'll call like an implicitly generated graph. And so this is when you don't necessarily have like all the vertices ahead of time, right? So like you don't know, or you don't want to store all of them, maybe. Like this comes up in games a lot, right? So if you think about games that progress through states, right? You can think of something simple like a Rubik's Cube, right? There are, when you're in a state, you can move to the next state if you turn it a certain way or turn it a different way, right? And you can make that into a graph. But depending on the size of the state space, and in this case, like the size of the Rubik's Cube, that's a lot of vertices. And you don't really need to have them all stored because you could compute them from where you're at, right? And so this comes up a lot when you're doing things like trying to write like an AI for a game that's going to play against someone or play against another AI, and trying to generate those states as a progression of whatever you're doing. So it's like you won't necessarily have this data, or you won't necessarily want to store all of it, just what's relevant. Okay, so today we're going to focus on one of the main questions that arises with the graph, kind of one of the first questions that we will come across and one of the most important ones. And that's how we can find a path from one vertex to another vertex. So it is a bit of a search problem. So here are some of the kind of questions that would get asked about a graph frequently. So the first being just, is there a path at all between two vertices? So is there any way to get from A to B? Might be a question. You might want to find all the ways you could get from A to B, because there could be a lot of them. Then what you're probably interested in is finding a path that has either like the fewest vertices between A and B that you have to visit, which we'll usually call the shortest path. Or if you have a weighted edge, or you have some measure, some heuristic of the cost of traveling between them, you probably would want to find the lowest edge cost when all those edges are added up together. And so that's more of an optimization criteria. And so you can think of that being like, I don't know, like the number of miles between two locations, or maybe the amount of time it takes to travel between two locations, and you want to optimize on keeping that low. So these are all questions that have to do with finding a path. And so we're going to look at two basic approaches today. Quick survey. Have people learned like depth first search before? Heard of depth first search? Okay. So we'll go through this. There's two very common ways to go about navigating a graph. And depth first search is the first that we're going to look at. So the idea here is that we say, like, since we have the graph, it's not like a tree. We don't have a clear route necessarily, right? But say we pick one, and maybe we're just trying to navigate, like these represent its locations, right? So we could just say we're at like location B or something. So that helps us start, right? We have a starting point. And we want to know if we can get somewhere else within the graph. And so obviously, what we can do is we can start to look to see who our neighbors are, right? But then we kind of have a decision to make, and that is, if none of our neighbors are the place that we want to go, well, we need to check their neighbors next, right? And we need to keep going in that fashion until we find the place we want to go, or until we run out of vertices, because maybe that place isn't connected, maybe it's not there, maybe it's not real. So what we need to do is we look at our neighbors, and then we have to decide, are we going to keep going down a path, or are we going to take a more gradual approach and look at all of the neighbors' neighbors? So in this case, if we're at B, and we start to look at our neighbors, right? Let's say we look in alphabetical order, maybe. So we look at A, and let's just say we want to go to D. So that's not D. So at this point, we could either say, okay, what are A's neighbors, which would be E, or we could say, okay, we'll just pause there and we'll check our other neighbor, C. So either we'll keep going in depth down the path, or we'll kind of gradually work our way out. So I'll give you some pseudocode intuition for this idea. If we have our graph, this is just a function, depth first search, and this is just going to traverse the entire graph, okay? So say we have our graph, we have a starting point, and then we keep a list of places that we've visited, because we only need to go there once. So the first thing we'll do is we'll say if our starting point is not in this visited list, we'll add it to the visited list. And then for each of its neighbors, we're going to do the same thing. We're going to do this recursively. And so what that will do is it will force us to go to our neighbors, 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 before we go like 1 degree out at a time. And so this will take, like say we have 3 neighbors, our first neighbor, we will go as far as we can on that chain before we come back and look at our second neighbor. And so that's the depth part of it, right, is that you're following that, all of the neighbors that you can get to first, rather than surveying the neighbors that are closest to you. So let's go through it on this graph. So this is a directed graph, and I've just got it in alphabetical order here. And so we'll say because it's directed, you can only go in the direction that the edges allow you to. So if we're going to go from A to H in this case, we'll start at A, and then we'll go in alphabetical order in terms of the neighbors. So neighbors of A, in this case we've got B, we've got D, and we've got E. So since B is first in the alphabet there, we'll go with it. And so we move to B. And then, since we're doing this in depth, we're going to go ahead and say, okay, for B, what neighbors does it have that we can get to? E. So it's got E, so we'll go ahead and follow that path. We'll get to E. We'll ask the same thing of E. What neighbors does it have? It only has one there. F. So we go to F. We ask that same question again. It has C. Go to C. And now we see that C has two neighbors, right? It's got E, and it's got I down here. Now E, we've already been to on our way here, so it's in our list of visited places. So as soon as we see that, we're not going there, because we've already been there. If we were to go there, you could see what could happen, right? We could just keep going around and around. So that eliminates E from places that we need to go. So now the only place we have that's a neighbor of C is I. We'll go down to I, but you can see that when we get to I, remember we're trying to get to H, we have nowhere else to go, and we haven't found H yet. So at this point, now we go all the way back. So we backtrack and bounce all the way back up to A, and then we say, okay, we've done B, what's your next neighbor, right? And so in this case, its next neighbor is for A. Yeah. D, yeah. So yeah, just doing it alphabetically, D. And also, you know, if you would have tried E, we've already visited it, so we wouldn't need to go there. But okay, so now we go from A down to D, and now we have two choices here. We'll do the alphabetical thing again, and we'll go to G. From G, we only have one choice, and that's H. And H is what we're looking for in this case. We have this target in mind, so we're done. And we can return the path from A to H. And so you can see it's really just this backtracking of where you've been is the path, so it's very easy to pull that path out because you've created this chain kind of as you go. So we've got this path, which is ADGH, and that will get us from A to H. Is that the only path to get us from A to H? No. Is it the shortest path?
No.
No. Right? So with the depth first search, you can find a path. There's no guarantee that it will be the only path or that it will be the shortest path. It will be a path. So you could continue to run your search to find a better path, maybe. But for the most part, this is kind of the mechanism of depth first search. And usually when you're using depth first search, you want just the first path that you can find. You've made that decision already. So the main idea being here that we go all the way as far as we can with our first neighbor before we go to our second neighbor and do that. So we'll find the path if it exists. It's very easy to return that path because you travel. Typically, it's implemented recursively, like the pseudocode. So it's very simple code, and it's very easy to trace that path back. But it's not the shortest path, necessarily.
Do we always do it alphabetically?
So you can decide what to do in an implementation, essentially. Like you usually would, if you're going to do like an ordering-based thing, like you would say if it's less than or equal to whatever it is, like if it's numbers or letters or objects. But you could also just do it kind of randomly, however, whatever comes first if you wanted. Yeah, because you don't really have any guarantees about what that path will be anyways, so any path would be good. And yeah, you'll see it implemented different ways. Yeah. So thinking about kind of the runtime of this, the complexity of it, we do this in terms of V and E, where V is vertices, E is edges, and typically you'll see them written with little absolute value symbols or bars around them just to say the size of, so the number of. And so the big O notation or big theta notation is usually written as a factor of V and E. So in this case, our runtime is actually V plus E. And if you think about that, that's because in the worst case, where there's something we're trying to get to that's not there, we would have to look at every vertice and travel on every edge. And so that runtime kind of changes depending on the density of the graph, right? Because like the number of edges could be a lot, it could be very little. And so that is kind of the driving factor in this, is the number of vertices, the number of edges. We know we're going to need to visit each of them once, kind of, in the worst case. And the same thing with space. So depending on how you kind of count it up, it can be a little bit different. But in general, the amount of space we need is V, so the number of vertices in the graph, because potentially our path could take us through all of them. Okay. Questions about depth first search? Are you ready to see an alternative to depth first search? No. Just going to stop it there. All right. So we have a different approach here. This is called breadth first search. So you will see them written just as DFS and BFS everywhere. And so the idea here is just kind of the opposite of what we just did. And so that's saying that if we're at location B, trying to get to D, rather than go to A and then go to E, we would look around at all of our neighbors, kind of in an iterative step, and then we would start with the first one and look at its neighbors, and then come back and look at the next one's neighbor. We wouldn't go all the way down that path. We'll just go kind of a layer at a time. And one of the benefits here, the main benefit, is that this will give you the shortest path in the number of edges that we have. So remember though, if these edges are weighted, if they have values associated with them, it may not be the shortest value path. This is just in the number of edges themselves between these vertices. So the code for this, pseudocode, kind of looks like this. And what we've got here, we've got our breadth first search function taking in a graph and a starting vertex. We're going to make a queue of places we want to visit, and we're going to make a list of places that we have visited already. First thing we're going to do is, in our queue of places to visit, we're going to put the place we're starting, and we're also going to go ahead and mark that place as visited. Then we're going to enter this loop, and all this loop does is, as long as we have places to visit still in our queue, we're going to visit the place that's next in the queue and check all of its neighbors to see if they're visited already. If they're not, we're going to add them to the queue to visit. So the queue is the driving data structure here, so it kind of gives you that assurance that the first things that you put in the queue will be the first things you visit. And so that ordering follows throughout this process. And that's what gives you the property of kind of doing like that fan out a layer at a time of looking at neighbors, because you're following this queue. So with the same directed graph that we used earlier, let's do a path from A to I in this case. So we're going to start at A, and we'll start to look at our neighbors. In this case, we've got B, we've got D, and we've got E. And so I'm just coloring these lines to indicate that we're aware of these, so they're in our queue at this point, if we're thinking about it that way. So we've scoped all of those out. The first thing we're going to do is go to the first one, which is B. And what we're going to see when we're going to ask B for its neighbors, right, to put in our queue. When we ask it, it says, well, I've got E, but we already know about E. E's already in our queue because it's a neighbor of A as well. So we don't need it twice. We'll just throw it away because there's no reason. So B has nothing else for us to do. So we're going to bounce back to A, and that means when we come back to A, we'll, bless you, we'll go to D next, right? And so we're at D now, and D has two neighbors. So in alphabetical order, G and H. So just shading those lines to indicate we're aware of those neighbors now, but we're not going to go look at them yet because we need to go back to A because there's still a neighbor at that level, and that neighbor is E, right? So now we're going to go to E, and we're going to ask what its neighbors are, and in this case, yeah. So F, so we will add that to our queue, and at this point, we don't continue forward. We need to kind of go back to what's in our queue, which can be hard to remember as a human being, just looking at this. So that is why it's nice to have a computer. But also you can write out the queue if you have to do this by hand. But if you remember, when we go back up a layer, we were at D. And so we'll start looking at its neighbors, which were G and H. So we'll start with G, and we will ask G for its neighbors. And what will it tell us?
You got one neighbor.
So yeah, it will tell us H, but we already know about H, right? That's already in our queue. So that's fine. We're done there. Then the next thing in our queue is, in fact, H. At this point, we're visiting H, and we'll ask H about its neighbors, and it will tell us all of these things, right? So it will tell us E, which we already have, so we wouldn't go there. It will tell us F, and then it will tell us I. Now, depending on how your code is implemented, you may detect at this point that you've found your goal, or you may go another cycle before you do. In our case, we're just going to go ahead and detect it as soon as we see that we have reached it there. So now we can return this path, and you can see that this is I, H, D, A. That's how we got here. And so in this case, is this the shortest path? Yeah, it is. So this will give you that shortest path. And that does make this a pretty powerful technique. So just a different way of doing this, instead of going all the way in depth into something, we're just a layer at a time doing this. So thinking about the complexity of it, so again, it's the same complexity as the depth first search, the number of vertices plus the number of edges, because if you think about that worst case, you do have to visit all of these things. And of course, the density contributes to this. So in large graphs, this can be a little bit expensive because you keep that queue of elements. And if that gets very, very large, like millions and millions and millions of elements, you'll need a little more space, but it's usually not that big of a deal. Are there questions about breadth first search and that approach to looking at elements? No.
I mean, you know what I'm saying? But we can test me on back to it.
Okay. So kind of pitting them against each other just to see like why would we use either, because like it kind of seems like depth first search might not be great if you're just like thinking about it like, oh well, it doesn't give me the shortest path, right? And if you're interested in the shortest path, then yeah, it's not great. But if you're in an application where you know that the path is going to be a pretty deep path, right? Like relative to the graph, like it's going to be maybe like most of the graph. Depth first search can make sense in that case. Remember, the runtimes are the same here, the complexity. So the worst case of these is the same number of operations that would occur. The main advantage that you're getting from breadth first search is that you're getting that shortest path. So depth first search is used a lot for games, puzzles, where things depend on the prior state, right? So if you think about chess, for example, like just a really basic example, kind of like, the saying like thinking however many moves ahead. literally however many moves ahead, right? And so the depth is that number of moves, right? But to do that, you have to compute what those next moves would be, which is a lot. So that's where we see like depth first search definitely very much used in games and puzzles, things like that. If you want to find a cycle, right? So if like your vertices are like say like files, like dependencies or something, like your header files or whatever you need for your code, and you want to make sure they're not like looping and pointing at each other in a horrible way, depth first search will detect a cycle really quickly. So breadth first search is obviously a huge advantage for if you're just worried about the number of steps to get somewhere, you'll find the shortest this way. It won't work for a weighted graph, but in a lot of cases, having a minimal number of steps is what you want. And if you know that your target is very like near your origin, then obviously you'll probably get on average a better runtime. Although remember, like in the worst case, it's the same. So that's all I want to do today. On Friday, your challenge is due, and we will kind of wrap up on graphs, the basic parts. And I think that is all I have, so I'll see you on Friday.